And what my plan today is to continue on the question of how we can deal with logical agents. So agents that take some knowledge about a game or the environment or rules and try to make informed decision on the basis of some formal system. And what we saw, I think, last time were the three elements of these formal systems that will help us to make those well understood derivations or entailments. And the three elements were that we needed to define unambiguously a language, like you have a programming language. The second element is that you need to assign for each of the valid sentences in this language some meaning. And that is the semantics. And the last thing is the calculus, where you want to have an algorithm that calculates automatically this meaning by some systematic algorithmic means. And today we are continuing a little bit with the semantics and then move to a first calculus if time permits. So remember the main idea of the semantics was that it's very difficult to define what truth in general means. So in this case, we want to assign semantics on the notion of a model, and a model is some interpretation of my sentences that is consistent with the knowledge bases that I have. Yeah. So I want to get back into this notion of the models and the entailments, but first I want to come back to this slide, which is the slide that I stopped with. And this slide was basically the definition of the semantic values of all of the sentences that you can write down in proposition and logic. Remember that we had looked at sort of formal systems in general, and then moved to a very typical canonical logic, which is called propositional logic, and try to understand how can we write down those sentences in the first place that are understandable. And then now we're at a state, can we also assign what they are supposed to mean in some systematic way? And remember, the kind of statements that we could make were propositions. So these were just atomic statements like, it is raining, card 7 is a jack, a pawn is on position 3, I'm a student or I'm a teacher. Both these things can be truth or false, but this is just the sort of the formalism that we now can assign to those propositional variables. That we can now assign values to those propositional variables, and based on the assignment of those variables, we can assign a value to a very complex formula. That is the idea. And this is the mathematical definition on how that works. So for each of the propositional variables, we can, as I said, assign either true or false. And then we're now talking about the composition of those propositions with something else. In the most simple case, it's this negation sign. And the meaning of this negation sign is now defined as its formula negation S is true if and only if the sentence S is false. So basically, the truth values turn around. And now, step by step, we define those truth values for the composed formula. And the important thing is that you have to remember that these S and S1 and S2 can now stand for arbitrarily complex formulae, and they are decomposed into smaller parts. And if you do that systematically, the formula becomes smaller and smaller and smaller until you end up with the propositional symbols. Okay, let's look at the first one, which is very simple. It is when is a formula S1 and S2 true? So that's this statement. And it is very, very simple. It is true if S1 is true and if S2 is true. So what happens here is that I have what's called an object language, an object logic, in which we use a symbol and we now translate this into some meta language, namely the natural language. So this and is now something completely different than this n. But we define the one in terms of the other, some meta system. Yeah? Now things become more difficult. And I want to switch now to some different way of looking at this. So if we have a formula S1, a sentence S1 or S2, then the question is, under what circumstances is this true or false? And the nice thing is that I can just take the two individual parts and go systematically through all the options. So I can look at S1 and I can look at S2. And I can say, okay, this one is true, this one is true, and then I'll use abbreviation capital letter T for true, and capital letter F for false, so that it's easier to write and read. And then I have 4 options. Yeah? That's clear. And now we can basically define what this S1 or S2 means by just giving all the possible values it can have on the basis of S1 being true and S2 being true. So if S1 is true and S2 is true, is then S1 or S2 true or not? True, yes. If S1 is true, S2 is false, is S1 or S2 true or false? True. Yeah, do I hear someone say something else? Okay, let me put a little question mark here. I'll follow it up later. The same here, it's just the inverse, and this is false. And yes, of course, you're right. There you go then. Yes, you're right, but if you think of natural language, I go to the bathroom or I go to the cinema, then this is usually not meant in a way that you do both. Yeah, so there is a natural language interpretation of or that might be different, namely exclusive or. In propositional logic, you are absolutely right. This is the way it's interpreted, but there might be some misunderstanding if you use this exclusive or option in your modeling. And this exclusive or option would then be, let's put it next to this as one, I think it's sometimes written like this, and this is true here and false in all other cases. Yeah? So this one is sometimes the one that we use in natural language and call it or, but this is the one that is really the standard propositional logic definition. You were all right about that. If you now look at the way this is defined here, S1 or S2 is true if and only if S1 is true. So that's these two cases. Yeah? Or S2 is true. So this is now this case. Yeah? In these 3 cases, I get the true here. True, true, and true. Yeah? So basically, what is written here is exactly the same as what's written here. So now that's why I put this on the board. I don't have a cleaning thingy. Here's this one. So let's get rid of this one, and let's move to the most difficult of all of them, because there's one that is sort of not trivial, and that is the next one. So we want to have a statement here that says S1 implies S2. So how would we write that? So if S1 is true and S2 is true, would you say that the statement, it rains, then I will be wet, and it's both raining and I'm wet? That seems to be quite a true statement. So now let's move to the case where something is false. So I have the rule, it's raining, so if it's raining, then I will be wet. Suppose that I'm not wet, but it's raining, then my rule is wrong. Yeah? So the condition is true, but the implication is not true means that this implication is wrong. So you find, in principle, you find a counterexample, namely this example here, where this is true, but this one is false. So now there comes something that is sort of disputed or not very natural in natural language as opposed to propositional logic. And this will all be discussed in detail in Van's course in period 4. This is just for you sort of to accept now. And that is that there is the assumption that if something is wrong, if something is false, you can derive everything. So if I have a rule, it's raining. If it's raining, then I will be wet. And if it's not raining, then this rule becomes meaningless, more or less, and it becomes true. So the statement, from falsity, everything follows. Yeah? There are some very good reasons why this is the case. This is the way that whenever you read a statement, phi implies psi, this is what's meant. Yeah? And I don't want to go into detail why this makes sense and how this is related to the relation between those two statements and so forth. There are very good reasons for this. For now, please just accept it and translate this into this definition of the implication operator. And just make sure that we understand that this is exactly the same. So we said that S1 implies S2 is true if S1 is false, or S2 is true. So we just go to this case. So this one is true. This is these two. This is these two. It's true. Maybe I should point this to the board so that you can also read and see it later. And the second case, so these were the two cases where S1 is false. So this one, S1 is false, or S2 is true. And the S2 is true case is this one. So we have these two. Yeah. So I just want to show you this truth table way of defining implication to show you that this is exactly the same that we have here. There are different. Is another way of looking at it. It could also be that it's false if S1 is true and S2 is false, which is exactly this case. So it's the inverse definition of it. So this is just the definitions of what or means, and means, implication means, and the equivalence means implication in both directions. And by that we have defined the meaning of propositional logic. Basically what we can now do is if we get such a formula like here, a composed formula, and you were right, these calculations were wrong, so I fixed them here in the slides. If we now have a truth assignment, so if we now know that P12 is true, P22 is true, and P31 is false, then we can just fill this into this formula. So we say not P12 is false if P12 is true. And then we put in the values here as well, false and true. Then we can look it up, false or true. False or true is false or true is true. So it's just looking up in the table, false or true is true. This one, sorry. And then we combine false and true is false. Again, according to the rule. Yeah?
In the example, we don't even need to evaluate the second part because the first part is false, right?
Yeah. So yeah. That is a more efficient way of doing it. But in principle, if you just fill in the values and you combine the things, you're done. And that's one way of looking at this. And this is one of the things I will ask you in the exam to do. So to get a formula, get some valuation, apply them to the rules. It's really principally simple. Just look at it, what it means. So that will be fine there. Okay, let's move on. So as I said, there is a notion of truth tables, which is used often to define the semantics of propositional logic. We use this sort of rule-based definition, but it's absolutely the same. And you will look in more detail in that in April, May. So what does it by mean? So basically, what I now want to check is whether I can derive some new facts based on this semantics, given some formal representation of the problems and the game state, for example, in which I am. And we are looking at a very restricted part of the model here, because if you do this on the whole 4x4 grid, it'll be extremely complicated. We look at a very, very simple model, problem here, and that is the left-hand corner of the Wumpus world. And I guess you still remember from last week that we had this exploring phase where there was nothing sensed in 1.1. So we walked in the exploration to 1.2, and we felt a breeze. So because we felt the breeze, the B there, we couldn't know whether going up was safe or going right was safe, so we went back. And then because of logical reasoning, we could know that this place was safe. Yeah. So now we want to find a representation, a semantic reasoning that allows us to conclude that this is safe. That's now our task. And all we're looking at is there somewhere a breeze or is there somewhere a pit? Yeah. So the breezes we can even ignore. We're now only looking at the options of somewhere being a pit. So we have 3 places where we can have a pit. So basically we have 3 propositional variables. Should do that again back here. So 3 propositional variables. What are the 3 propositional variables that we are working with? Somewhere being a pit. So it was P. And we're just looking at the ones with the question mark. So it is P21, and it's P22, and it's P3113. Yeah? This is our 3 propositional variables, and they can be either true or false. And now we want to have a knowledge base about the game that tells us whether, this is going to be the question, is this one true or is it false? Because if it's false, if we know that it's false, then we're safe. Yeah? That's our question. So we want to find out whether P21 is always true in this situation. So let's look at all the possible situations that we could have given these 3 open fields in the drawing or our 3 propositions that we have. So we have the situation where this one could be true, false. This one could be true, and this one, true or false. Yeah? So basically we have 8 possible combinations. Yeah? 2 to the power of 3. And these are the 8 possible combinations. So this is what we know. So this will not change. So we have nothing here, we have a breeze here, and now the question is, where could be possible pits? And we have the possibility that there is pits everywhere, that pits nowhere, that these 2 have pits, these 2 have pits, and these 2 have pits. And then we have the 3 other options where it's just one pit. This is all the 8 options we have. Yeah. So now comes the idea that we know already something about the game. So some of these 8 states that we have here, these 8 interpretations of the world, the possible world, as you could know them, are not consistent with the knowledge we have about the game. Which one are not correct given the knowledge that we have about the game? The middle one. Why? Exactly. So we know that there is a pit, either here or here. Yeah? Which one is not correct?
Second one.
That's the second?
No,
that?
From the right. So first one, yeah.
That? Yeah. Why is it not?
Because you know there is a pit in 2.
Yeah. So basically what you said means already that there needs to be a pit in either this one or this one. Yeah. So otherwise there couldn't be the breed here. So basically there's only those three of the possible worlds consistent with the knowledge we have about the game. Is that clear? Yeah? So these three models, these three interpretations here are called the models of the knowledge base. So these are the interpretations of the variables which are consistent with the knowledge in my knowledge base. So basically they satisfy all the axioms in my knowledge base, where the knowledge base is the 1 plus world rules plus the observation that we have about the position 1, 2. Okay, and now there comes a definition, something you really have to just learn by heart. This is the most important logical notion that will come back and back and back again, and that is the notion of entailment. And that basically in informal terms means that a fact alpha follows from the knowledge base. In technical terms, the knowledge base entails a fact alpha. And the definition is that a knowledge base entails a fact alpha if and only if it holds in all models. So in all the worlds that are consistent with the knowledge base. And this is a very powerful notion. We're going to show how to calculate entailment, and we show how to relate this to other reasoning tasks. But this is the definition you really will encounter again and again. It's a very powerful, and I will just show in a minute how we can now calculate entailment based on the models that we've seen before, and how we can now derive that the fact that P21 must be safe, how that follows by the notion of entailment. So basically what we want to show now is the knowledge base consisting of having all the rules of the game plus the observations in the game entail the fact that P21 is safe. And then your logical agent just needs to check whether this is entailed, and if it is entailed, then it knows that it can move. So how can we now, how does it work with this notion of entailment? So basically, we said that in all the models of the knowledge base, something has to be true. So here comes the question, is point 1, 2 safe? In other words, does the proposition 2, 1, not 2, 1 holds? Yeah, because we want to be sure that there is no pit. So safe meaning not a pit. So we have to show that in all the models, in this situation, in this position, in 2, 1, there is no pit. Yeah. So if we now take all the models for the knowledge base, we simply check the value of P21. And this one is no pit, it's safe. This one is pit, no pit, safe. And this one is pit, no pit, safe. Yeah. So we're just looking at the models of the knowledge base and check whether something holds in all those models, whether they have something in common. Yeah? That is the argument that I was just about to make. Yes? So what we've just seen is only looking at the red things, ignoring the yellow line. We can still already check whether in all the models of the knowledge base, this is a safe space. There's now a sort of inverse way of looking at this, and that is one way of making this more algorithmic, and that is to say, let's look at all the models of alpha. Yeah? And that is basically, let's look at all the states in which alpha is true. And if this set of models of alpha is a superset of the models of the knowledge base, then alpha is entailed. Yes? So basically what I do now is I draw the yellow line of all the places where alpha 1 is true. So basically here it's not true, here it's not true, here it's not true, and here it's not true. But in all the others. And then I have the yellow collection of states. And then I just have to check whether the red thing is a subset of the yellow thing. And that gives me the algorithm for checking entailment. Yeah? That should be the answer to your question. Yeah? Okay. So let's take this algorithm and apply it to a different problem. And that is the problem whether 2 is safe. And as I said before, let's look at all the states, all the assignments where 2.2 is safe. And that is this one, this one, this one, and this one. And if you now check whether this one is a subset of this one, then it's not the case. So the algorithm of taking all the models for A2 and checking whether the models of the knowledge base are a subset of it fails here, which tells me that this is not the case. So A2, 2 is safe, alpha 2 is not entailed because there is no subset relation between the red one and the pointed line. And why is that the case? Because we have a counterexample, one where we have something that is consistent with our knowledge, namely these two, but these two are counterexamples for alpha 2 being false. There being a pit in alpha 2. So it's not a safe place. Yeah? So because there is not this subset relation between this line and this line, we cannot derive entailment. But in the other one, we have the yellow line around the red one, and that means that the red one is a subset of the yellow one, and that means that we have the notion of entailment. So, in a way, it's very simple. Entailment means that something being true in all the models. So what you have to do is to either go through all the models and check whether the formula is true. What you can also do is that you check all the models for the formula and check whether the models of the knowledge base are a subset. There are two different ways of doing exactly the same thing. Okay. This is something you just have to read up 3 times until you believe it. There is nothing to understand, or so this is the definition of the notion of the definition, but this is something you have to just learn. Something that is true in all the models, and that's something you have to drum up in your sleep for the exam. Based on this notion of entailment, we can now do loads of other things, and based on the notion of models in general. So if we have a sentence that is true in all possible models, so not only with respect to some knowledge base, then this is called tautology, or the formula being valid. So if you have the statement A or not A, so something being either it rains or it doesn't rain, is one of those tautological statements which is always true. Because basically whatever value I give to rain will always end up in a true formula. So all the models of the statements, everything is a model for this statement. That's what I wanted to say. Whatever you give it a value true or value false, it always is a model of this statement. So it's a valid statement. Satisfiability is another very important notion in logic, and that is, can I find for some formula a value that makes my formula, my complex formula, true? So basically, the opposite of a tautology would be unsatisfiability, the last statement, where you find an assignment of values for which there is no model. So these are the 4 notions that you basically have to learn and have to be able to answer whether there is a model, which then it's satisfiable, whether there's no model, then it's unsatisfiable. And if it's always true for any assignment that you can find, then in all models, then it's a tautology or it's valid. And we're going to practice those notions in the working groups so that you can just, given a formula, tell me whether it's satisfiable, whether it's unsatisfiable, whether it's entailed, and so forth. And the nice thing is now that this notion is well defined on any formula in propositional logic, and we can now find algorithms for it to reason automatically and to tell us for any propositional formula that you give me. My algorithms that I'm going to show you in the second half of the lecture will give you exactly the answer. Oh yeah, this is entailed and this is not entailed. So we can basically leave the decision of whether a space in the game is safe or not, we can leave to an algorithm. That's quite intelligent in a way. So we're not looking at it by understanding the game anymore. No, we've done that when we model the game. But the decision on whether it's safe or not, that's our algorithm doing the job. This algorithm is called the calculus, and I'm going to the calculus in the second half, but I still have two slides I want to look into, and that is some pros and cons about this logic. And the one thing is the notion of declarativeness, so that you really describe the semantic in an explicit way, so that people can look into it, could look at it and say, okay, this is what you mean, this is this is your intention, these are the operators and so forth, which something you don't have in machine learning very often, because you might learn, as I said this morning or this afternoon, you might learn an equation or a hyperplane where you have sort of explainable parameters, but even there it's quite difficult to understand, and in most cases the meaning somehow emerges from observations and pattern matching or clustering. Here it is really declarative. Right from the beginning, you write down the knowledge explicitly. And you can model uncertain information to a certain degree. You can say, I have 3 notions, but it might be a fourth one. So either there is a pit or there isn't a pit. I simply don't know yet. So you can use a disjunction to model some uncertainty. You have negation. So in a database, it's very difficult to say that something is not in the record of a database, these kind of things. The compositionality is very important, so I can combine complex formula to another more complex formula, and I can calculate from all these complex combined formula, I can calculate the value, the semantics for these complex compositional formulae, which is something you cannot always do in natural language, for example. There's very often that you cannot take the sentences apart and still know the meaning. And this is very computationally very nice. And in principle, unlike human natural language, you do not need any context. So we get some assignment. We don't need to understand what P21 is. We still get the result P21 is true in my models. I don't need to understand that there's anything about pits or breathers or the numbers. As long as this is in my model, in my knowledge base, then I can reason over it. I don't need to understand what the meaning is of the terms in the language, which is quite handy very often. But, and there is a big but, so we have nice properties, but if you really want to express something powerful, already like the Wumpus world, it really becomes very, very messy very soon. Let me show that with the idea of the Schnapsen. So if we now think of modeling Schnapsen, then there might be some strategies we talked about. You gave me in one of the lectures, I think last week, you gave me one of the strategies. For example, you want to you play a Trump wedding. What does the Trump wedding mean? It means that I have a card, which is the queen. It is also Trump, and there exists something which is has the same color. So it is also it's also the Trump color. It's a king, and I have it in my hand. Yeah, it might not be the best way of modeling this, but this is all the information we need to model that I can play now a card in a Trump wedding. These were, I think, all the things I needed to say. It's a queen, it's a Trump, there is something of the same color, which is a king, and it's even on my hand. So now I can basically check all my cards, whether they are a Trump wedding, and I can just do that by checking, is the statement Trump wedding of my card? entailed by the knowledge base that I've given about Schnapsen. Sounds great, but there is a big problem, namely I need to define this for all possible X, for all possible cards. So if I want to write a knowledge base that has only this fact, I need to write trump wedding of card 1, if and only if Q of 1 and trump of 1, and then it becomes even more difficult because now I have to do it for all the Y. So now I have to write down if either same color 1, 2, and K of 2, and then I have to do the same for 3, and I have to do the same for all the other 19 cards, and I have to do that for all the 19 cards, for all the 20 cards, just to model this one bit of idea what a trump wedding is. So basically I have 20 times and then 19 faculty different things I have to specify. So it becomes already huge. So what if we had a language that would say a trump wedding for X, for all X, is something where this X has to be a Q, and so forth, just as it's written down with the exist statement here. So that would be so cool if we had such a language. And of course, this language exists. So this is predicate logic, and you're going to deal with predicate logic in logic in sets. So there are logics that are more suitable for modeling this stuff, like for a Schnapsen game, or because you can talk about all the elements in your domain at once, in one statement. And that's what you basically get in first order logic, as it's called, as a method for representing information about finite or infinite domains. Okay, so I think it's a good moment to stop. I would appreciate to have, let's take 10 and start again at 5, because I started so late because of the technical problems. Okay, 5 o'clock. See you.